Okay, good afternoon once again. So let's continue from where we left off last time. We were using the wage dataset to predict the dependent variable that we were considering is our wage. Okay, so let me just flash. Here's our wage data. This one. Okay, our dependent variable was hourly wage, and then we regress it on education, experience, tenure, number of dependents. Okay, 4 quantitative variables and 3 categorical variables. What we learned so far was that in the new version of RStudio, you don't have to convert this to factor. R will automatically convert that. But of course, we can on our own also convert that just to be sure. Just to be sure that the variables are already converted to factors. So let me see. Let me do that just to be sure. It's supposed to be at the start. So this is a quick review of what we have discussed so far. Okay, I hope that with the constant use of R, you're able to gain competency and you're more, let's say, comfortable using the package here. Okay, so for categorical variables that can be used as factors, we said that we should convert them as factors because the older version of R will not allow us to use as independent variables, as predictors, any categorical variable. So we only use categorical variables that can be classified as factors. Otherwise, there's no point in using it as a predictor for your dependent variable. So if I run this, and if I just check one, so class, wage data set, and then let's see here, race. Let's see if this was called. So it's already a factor. Okay, so I'll dispense with the other models. The last model that we looked at was model number 5. Okay, and then if you recall, we did what we call stepwise regression. And we also tested the models. Okay, so this is model number 5. I'll run this. Okay, so this is our result. We can see that our predictors, education, tenure, gender, and civil status are all significant. Okay, and so we don't have any variable to remove. So this is our final model, and as I mentioned, they're all significant. And just a quick review, how do we interpret this? We said that these estimates present to us the marginal effect of your predictor, in this case education, on your outcome variable, which is hourly wage. Okay, it's the marginal effect. It's the effect of 1 unit increase in education. Okay, and its effect on hourly wage. So we say that for every 1 year increase in education, there's a corresponding $0.53 increase in hourly wage ceteris paribus. Ceteris paribus indicate that we're not going to change, we're not going to add, for example, we're not going to add 1 year in tenure. Okay, so we will let that be constant. That's why we add ceteris paribus. So also for tenure, 1 year increase in tenure would mean a $0.15 increase in hourly wage ceteris paribus. And then we also learned the interpretation of dummy variables. Okay, dummy variables are the factors. And as if you recall, R automatically makes the level. For example, in gender, let me move this here. For gender, there are two levels, female and male. What R does is that it automatically makes this is the benchmark, which means it makes this 0 and the male is 1. So also recall that for category for factors, we only introduce k minus 1 dummy variables, where k is the number of levels. So back again to my example, our gender has two levels, female, male. Therefore, it will only introduce one dummy variable. Why only one? Because it already accommodates all the levels. Okay, with one dummy variable, you have for female 0 because it appears first, okay, and male that will be 1. So no need to have another variable here. Let's say here female and here male. No need to do that because these two are the female and the male are perfectly correlated. So we will have a problem with multi-collinearity. Okay. If I introduce male here, okay, so let me just annotate this. Okay, let's suppose instead of introducing just one dummy variable, I have here female and then I have here male. So female will be 1 and male will be just the difference between the female minus 1. So this will be 0. Okay, so this will be again 1, 0, and then male is 0, 1. Okay, so notice we're not introducing two dummy variables because this will actually be correlated. These two are perfectly correlated. Okay, so remember, one of the assumptions of multiple linear regression is the problem of multicollinearity, which we stated that the independent variables should not be correlated. If you get the correlation of this, you'll get -1. Perfect. So -1, this is perfect correlation. Female and male are perfectly correlated, so we will have problems with our model. That's why we only introduce k minus 1 dummy variables. So if there are 5 levels, then you should only have 4 dummy variables. Okay, let me pause for a while. Is that clear, class? Just a quick review. Kindly chat, please, if that's clear. All right. So, okay. So back to our output here. Okay, so this is our final model, and we know how to write the equation. Okay, by the way, what's the meaning of the dummy variable here? The 1.7. How do we interpret that? This one, 1.7. Okay, we always interpret our dummy variable in relation to the benchmark. The benchmark is female, which means this was made to be 0. Okay, and R, what's good with R is that it has a convention of putting here gender male, which means you interpret this as male, but relative to female. So this is telling us that on the average, male employees tend to receive $1.71 more than their female counterparts, okay, ceteris paribus. Also, single employees receive 0.68 or 0.69, approximately $0.69 less than their married counterparts, ceteris paribus. Okay, so those are the interpretations of your dummy variables. And lastly, the intercept. How do we intercept this? Although we don't have any practical there's no practical interpretation for this practical meaning, but if we're including the intercept, and we said even if it's not significant, but in this case it's significant, but if it's not significant, then we still include it in our model. So this means that this is the average, okay? This is the average hourly wage of an employee who has no education, 0 years of education, 0 years of tenure, who is female, okay, who is married, okay, who is female and who is married. Okay, how do we know that? Because take note that the intercept is interpreted as the average value of your dependent variable, which is hourly wage, given that all your parameters are all 0. So that means 0 years of education, 0 years of tenure. Now, gender male, the 0 there is female. So that's why we're interpreting it as a female and then also a married employee. Okay, so that's how we interpret the intercept. Okay, so we compared using ANOVA, Model 4 and Model 5, and here, what do we have here? Okay, let's run this. Oh, sorry, I don't have Model 4. Okay, I think I have to run Model 4. So let me run Model 4 first, so that we're able to compare it. So this is my Model 4. Our Model 4 includes experience, but experience is not statistically significant. That's why it led us to delete experience to come up with Model 5. And then, how do you know which model is better? There are several ways to do this. We can use AIC. Okay. By comparing AIC, we notice that model number 4 is preferred to model number 5, because for AIC, the lower the better. But a more stringent way to test which model is better, so we use the analysis of variance. Here, the null hypothesis is that the restricted model is the one with the lesser number of predictors. Okay, so in this case, model 5 is the restricted model, and model number 4 is the unrestricted model. Okay, so it turns out that the p-value here, the f-stat is 2.42, and then the p-value is 0.11. Therefore, we said that if the p is low, the null must go. But here, the p is greater than 0.05. Therefore, we fail to reject the null hypothesis. Okay, so we cannot reject the null hypothesis that the restricted model is preferred over the unrestricted, which is model 4. So our choice is model 5, the restricted model. All right, and then we went to the automatic way to do the stepwise regression, because we said that we were doing that manually. Okay, so here I'm identifying our model. Our model is the LM, hourly wage on all the variables, data is equal to wage. Then we can do this. No? We can do this forward stepwise regression. Okay, and the function is OLS step forward underscore P. Okay, using the P value. Okay, we did this last time. Okay, so just a quick review. Okay, then let's get the summary of this. Did I run the model? Yeah, I think I ran the model. Okay, so this gives us the final result. So these are our predictors: education, tenure, gender, and civil status. Sorry. Initially, we just add education because this is forward stepwise regression, which means that we're adding one variable at a time. Then we add the tenure, gender, and then civil status. And other things that we can, right? So this is just a summary output. Of course, we can get the step by step. Okay, how did we get the step by step? Okay, here, no? Details is equal to 2, but let's not go with that because we already discussed this. So what we did was forward stepwise regression using the p-value as our basis and also the AIC as our basis. So we said that this is similar to model 5 and model number 4. If we were using the AIC, the suggested model is model number 4, which included experience, although experience was not statistically significant. So the basis of the choice was the Akaike information criterion. So take note that the AIC method, if we choose that, it will suggest to us that the best model is the one that has the lowest AIC, even if the last variable is not statistically significant. On the other hand, yung p-value natin, p method natin, which we used here, how do we know that? Here. AIC ito. Okay, ito, no? Yung basis natin. This is the function OLS step forward underscore p method. Isa naman OLS step forward underscore AIC. And this is our basis. A variable will only be included if the p-value that results is less than 0.05. Okay, then the other is the backward. Okay, did we run the backward regression, guys? Paki-chat, please. Because I told you actually to work on that. No? I think we only run forward p value and forward AIC. Could I have, guys, some confirmation from you if we run the backward? Okay, forward. Okay. Bakit nagko-conflict? So forward lang ba o pati backward? Kasi if we already did the backward, I won't. Anyway, okay, let's see. Forward lang. Sige. Okay, so let's do the backward. But the backward we already know kasi that's what we did last time. Huh? So, okay, where's that? Forward. All right, here. Backward regression using p-values. So the function is OLS step backward underscore p. Okay, we're creating an object called backward fit.p. Okay, and then since this is backward, the function to be used is p remaining and not p enter. So forward we use p enter. Okay, so that's the difference. Here we use p enter. Here we use p remain. So which means a variable will remain as part of the model if its p-value is less than 0.05. So if I run this, okay, we'll now have the elimination summary. So elimination summary, this means that these are the variables that were eliminated one at a time. So step 1, race was removed. And if you check yung manual regression na ginawa natin, indeed, race was the first one to be removed, and then number of dependents, and then finally experience. Okay, and you can see here that the adjusted R squared, okay, it will go down, of course, because the more variables you have, sorry, the R squared, the R squared, the more variables you have, the higher it will be. So that's why this is going down 37.03, 3682, 3652, but not necessarily for the adjusted R squared. Okay. So if we add a variable, okay, for multiple linear regression, what's more important for us is the adjusted R squared. And if you know, the R squared will always be greater than the adjusted R squared, because we said that adding more variables, when you add more variables, it necessarily your adjusted R squared goes up. However, what we're more interested in is the adjusted, because we're going to penalize the our model for the use of more independent variables. Okay. All right. So here, okay, let's not run this because it includes all the details, step by step talaga. Okay, so I think I illustrated this to you. So I'll just leave you to run this class. It's the same as the one above. Okay. Sige na nga, run ko na rin. It's quite a long process, but it gives us the very details by which the process of elimination was done. So first you have, as your regressors, all the independent variables. Okay, so since for backward regression, backward stepwise regression, we start with all the variables and then eliminate one by one. Here, X race, which means we're going to eliminate race. Okay, so we're eliminating race, and then these are the result. If we eliminate race, R will be 0.609. Okay, this is correlation, and then adjusted R squared 36.3. Then we have also root mean square error. Okay. And then next, we remove race. Oh wait, ano nangyari dito? I think I skipped some lines. Okay, and then it gives us the values of your parameters. And then, skip yata yun. So may output ka, wala. Wait. Okay. Backward. It's not showing there, so dito ko lang pinapakita. So here, step by step, guys, just like the one that we did before, kung ano yung mga remove, raise, remove. So here, remove yung raise. Then it gives us the ANOVA and then the output. Wait. What raise lang na rin? Is something wrong with my model? Dali lang ha. Kasi raise lang na-remove eh. How about in your case, guys? Dapat ma-remove yung ano, di ba? Dapat tatlong variables yung ma-remove. What's wrong with this one? Backward. And model, tama naman yung model. Model is this one. Early wage education. Okay, how about in your case, class? Kasi I'm getting a strange answer. Ay, wait. Tama ba? The backward. Backward to. So, pag backward kasi, we start with all the variables and then remove one at a time. Pero bakit raise lang yung natatanggal sa akin? So, let me run this again. Elimination summary. Ito, no? So, sinamarize na niya. First, remove the race, then number of dependents, then the experience. Okay, backward elimination. Race muna. Tapos, bakit variables race lang? Okay, strange. Guys, pa-check nga yung ano, yung output nyo. Kasi ang lumalabas lang sa akin, i-eliminate lang si race. We are eliminating, this is a strange output. Race lang yung tinanggal. And then, if I go down, sabi, no more variables. Variables remove, race lang. Take a look at the summary here, guys. Look at the elimination summary. Race muna, tapos number of dependents, tapos experience. So, tatlong variables yung eliminate. No? So, dapat dito, pag tinanggal na niya, race, dapat susunod yung number of dependents. Pero, no more variables satisfy. P-value is equal to 0.3. Bakit 0.3? Wait, ha? How about the others, guys? Comment nga, please. Are you also getting the same output as me, guys? Bakit ganun yung backward natin? Yeah. Bakit? Hindi dapat ganito eh. How many times have I done this and it gives us the correct answer. Pero ngayon, I'm surprised why ang tinanggal lang niya race. Sige, anyway, tingnan natin yung iba. Tingnan natin itong si backward din, pero based on AIC. Let's check this. Based on AIC. So the basis is this one, no? AIC 2640 Okay. So pag tinanggal daw si race, magiging 2638. Pag tinanggal si number of dependents, 2638.6. Okay, and then if we plot, so makikita natin dyan kung sino yung pinakamababang AIC, no? So tinanggal race, tinanggal si number of dependents. Hindi tinanggal si experience. Dapat tatanggalin si experience, eh? Kasi para model, oo, dalawa lang, no? Ito tama, guys. Dalawa lang tinanggal, race lang at saka si number of dependents. I was thinking of backward using p-value. So this one, tama ito, no? This is similar to model number 4 na yung experience kasama pa rin based on AIC. Okay, so yung backward P lang yung no, yung medyo problematic. So I don't know, guys, kung bakit so let me first check that. Tama naman, no? Okay. All right. So far we discovered that for backward stepwise regression, we're having a problem with the p-value, no? Yung p remain. Okay. So let's just move on first, no? So we can also use both fit. Okay. So itong both fit class, parang combination siya ng ng forward at saka backward. So let's do this. Okay. So yung both fit class, parang pareho lang siya sa pareho siya sa forward. Okay? Pero ang forward, pag tinanggal na yung if you enter a variable, it cannot be removed. O ganun sa forward stepwise regression. Sa backward ganun din. If you remove a particular variable, hindi na siya pwedeng ibalik, no? Sa forward, di ba magdadagdag tayo isa-isa. Once you add a variable, it's no longer removed, no? Ito, pag both, pwede kang maglagay ng variable, tapos pwede mo rin siyang tanggalin. So that's a difference between the both and forward and backward. So dito, in-add si education, in-add si tenure, in-add si gender, in-add si civil status. Take note, wala siyang tinanggal, no? But it can. Yun ang characteristic ng both, no? Both ways. Okay, stepwise regression lang, parang generic in general. Kasi isa forward stepwise regression, tapos yung isa naman backward stepwise regression. Ito stepwise regression. Okay, it's similar to the forward since it starts from nothing. Tapos magdadagdag siya, pero pwede siyang magtanggal para papalitan ng isang variable. So that's a difference between yung stepwise at saka yung forward stepwise. Okay, this time this is the AIC method. So let's run this. So itong both. Okay, ganoon din. Nagsimula, no? Education, in-add. Tapos in-add si tenure, in-add si gender, in-add si civil status, in-add si experience. Okay? And it gives us the lowest AIC. 2638. Although ito experience, no, hindi na sa statistically significant. But since we're using AIC, pinasok pa rin natin siya. Okay, so yung stepwise regression class, medyo similar siya kay forward. Again, the only difference is kay forward, kapag nagpasok ka ng variable, hindi mo na pwedeng tanggalin yan. Okay, stepwise, pag naglagay ka, pwede mong tanggalin siya, pwede mong palitan ng iba. Okay? But in this, in our data, wala naman siyang in-add tapos sinabtract. So, lahat in-add lang niya. Okay? So, if we plot yung method ng both, you can see na, okay, both fit. So, in-add si education, and then in-add si tenure, in-add si gender, in-add si civil status, in-add si experience. Bakit kasama si experience? Kahit na hindi ito statistically significant. Kasi ang basis niya, yung AIC. As long as bumababa yung AIC. Okay yan. Okay, and then we can have here the details. No? Alright, hindi ko na i-run yung details. And then we have here all possible subsets ng regression. Ito, very comprehensive to. No? So let's just take a look at this. I-run natin to, medyo mahaba dito. Okay. So this includes all. No? Kung isang predictor lang, ano yung pinakamaganda? Kung dalawang predictor, okay, so take a look at this. Okay, and dito ibig sabihin ilang predictors. So kung isa lang, isang predictor lang, sino pinakamaganda? So we have R squared, adjusted R squared, and Mallow CP. Okay? So hanggang Mallow CP lang. So this tells us, in terms of adjusted R squared or Mallow CP, sino yung pinakamaganda? Siyempre, the higher the adjusted R squared, the better. So it turns out that education, based on adjusted R squared, is the best. And based on Mallow's CP, it's the best. Kasi parang AIC to it. The lower, the better. Okay? So, and on, guys. No? So, kunyari, dalawa naman kailangan. So, ipapakita dito yung combination. Education tenure, so una siya. Ibig sabihin, ito yung pinakamaganda. If there are two predictors lang. Adjusted R squared is 0.299. Susunod, 0.255 lang. Mallow CP is 54. Okay? So it gives us yung combinations ng mga So very comprehensive siya. So lahat ng combination ng dalawang variables, ipagsasama-sama niya, tapos it will tell us which is the best one. And it comes at sa unang-una, it's presented first. And this is presented from best to worst. So pag tatlong variables daw, education, tenure, and gender. Ito yung model na pinakamaganda, having the highest adjusted R squared and the lowest Mallow CP. Okay? So very comprehensive, Grabe, lahat ng possible combinations ng mga regressors. So 3 pa rin yan. So okay. So marami kasi possible combinations. Pag 4, this is the best combination: education, tenure, gender, civil status. Okay, and then this is our adjusted R squared. This is our Mallow C. Okay, and tinuloy pa niya, Kung 5 naman, kung 5 yung isa papasok natin, ito, kasama si experience. And then kung 6, ito, ang tinanggal si race, diba? Sa backward stepwise regression, yun yung talagang tatanggalin. And of course, lastly, pag 7, kasama lahat. Kasama lahat. Okay, so that gives us the result for dito sa function na to. here. Yung model compare, no? OLS step all possible. So this is the function. Okay, then we can actually convert this into a data frame. So if I run this, and then let's see, mod compare, view natin siya. So naging data frame na siya. Ito si mod compare, no? So let's have it printed as an Excel format. Okay. So convert natin as a data frame. So ito yung mga, these are the measures. $127 possible combinations. Okay, starting with one predictor hanggang lahat ng predictors. So we can actually download this. Write this as an Excel file, and then we can have a copy of this. Okay. All right. Okay, so we now go to residual analysis. I think this is a very important topic kasi our final model is model 5. Summary lang natin. So this is our model 5, but we're basing it on p-value. So we have 1, 2, 3, 4 predictors. Okay, the individual t-test tells us that all the predictors are statistically significant, some at 0.001, some at itong civil status, significant at 0.05 level of significance. Then you have this overall goodness of fit test, where we're testing if beta 1 is equal to beta 2 is equal to beta 3 is equal to beta 4 is equal to 0. And then our conclusion is F-stat 74.95, degree of freedom 1, 4, because there are 4 predictors, degree of freedom 2, 521, which is n minus k minus 1, ilan ba yung n natin? 526 minus k, number of predictors, which is 4, minus 1. So we have 521 df2. And then the p-value is practically 0. Okay, significant, 3 stars to, no? Significant at 0.001. And we reject the null hypothesis that the predictors are all 0. Okay, there's statistical reason to believe that at least one of these predictors is not equal to 0. Okay, so yan yung model natin. Now, if you take a look at ito nagawa na natin ito dati. Pero, ano ba yung laman ng model 5 natin? Let's just have a quick review. Model 5. Right, so these are the elements of model 5. Okay? Now, it's important for us to, hindi pa pwedeng, we cannot just stop there. What we have to do is to, okay, what do we do, guys? We have to test whether our residuals are okay. And ang tawag natin dyan, class, is diagnostics. We will have to conduct model diagnostics and test kung okay yung model natin. Okay, so sinummarize natin yung model natin, di ba? Ito yung, if we take a look at, let's access yung ANOVA. Kunin natin si ANOVA. Kasi dito sa dito sa summary natin, hindi binigay yung analysis of variance. Ito yung ANOVA, no? Kaso hindi siya in itemize. So let's get ANOVA. All right. Sorry, hindi pala yung ano. Hindi yung okay, my mistake, no? So yung analysis of variance natin binigay sa summary. It's this one. Okay, I was looking at the F-stat. Okay, so yung model 5, guys, it gives us as we have shown yung mga names, maraming laman yan, di ba? Andiyan yung mga residuals, andiyan yung predicted values. Okay, in fact, let's check yung residuals and then model number 5. Just by way of review, ibibigay sa atin, no? Yung lahat ng residuals. And there are 526 observations, so you'll get 526 observations ng residuals. And then that's the same for the fitted values. Fitted model 5. Kasi yung sa names natin, dyan si fitted, no? Fitted.values pala. Pwede ba itong fitted? Pwede. Yung function fitted. Okay, but if you want to get the fitted values, pwedeng ganito. No? Pwede rin ganito yan, guys. No? Yeah, it will give us the same thing. So ito yung function of fitted ng model 5 or model 5, yung names ng mga objects na nasa model 5 is fitted.values. Okay, and we know that the nature of OLS, tuloy natin yung mean ng residuals ng mod 5. So what will this give us? Parang mali yata. Wait, residuals yan. I'm getting the mean. So dapat isang value lang yan. 0.126 sa moment, guys. No? Okay. So itong residuals, pwede natin yung first 6. 0.126, no? So these are the first 6 residuals. But if I get the mean, okay, I should get 0. Practically 0, guys. Remember, yung mga residuals natin, di ba? When you get the average of that, it will give us 0. Okay, so this is what I was trying to run. Kanina binigay yung yung residuals. Okay. All right, sige. Let's go here first. Let's plot the residuals. We can use the plot function. Okay, so gamitin muna natin si plot function. Plot, then mod 5. This basic command will give us hindi pati autoplot, no? Okay. All right. So binibigyan tayo ng ilang plots dito. Iba-ibang plots, no? Number 1 is one of the most important plots sa residual sa diagnostic analysis. It's the residuals on the y-axis versus the fitted values, the predicted values on the x-axis. Okay, kasi this will tell us a lot of story. Number 1, it will give us candidates for outliers and influential data points. Titingnan natin to next meeting kasi it's almost time, no? But let me just tell you that sa diagnostics, we will go back to our model and then test or validate it whether it complies with the assumptions of the classical linear regression model. So ano ba yung mga assumptions natin? Number one, linearity. Linear ba yung relationship ng independent variables natin at saka dependent variable? So makikita natin dito yan sa residual analysis. The first plot is the residuals versus fitted. It already gives us also an indication, linearity, and this one also tells us of the kung heteroscedastic yung distribution ng error terms natin. In fact, dito pala makikita na natin na medyo heteroscedastic to kasi, take a look at this, may fanning out. Hindi constant yung variance natin. Our variance, let's call it sigma squared sub I, okay? It's not equal to sigma squared. Ang homoscedastic, guys, ang variance constant kasi dapat, sigma squared lang. Ito, yung sigma squared natin sub I, no? Ibig sabihin, it's dependent on the predicted values. Kasi dito sa point na to, at this point, yung average natin ng variance, diba? Dito eh. Okay? Pagdating sa point na to, diba yung average variance natin, no? Ang laki na. No? Dito, at this point, dito lang. At this point, dito. Yung congregate, yung nagko-congregate yung ano natin, yung residuals natin. So, for a model, for the residuals to be heteroscedastic, dapat yung variance ang ganito. Sigma squared lang. Constant, no? Wala tayong I dito. Heteroscedastic pag ganito. And we don't want that. We have to address this. So it looks like hindi homoscedastic yung error terms natin. Now, uunahin ko lang, guys, na ang heteroscedastic na residuals natin, it can be a symptom of something that's wrong. So perhaps sa model natin, dapat ba may transform tayo? Should we have been using the log of number of dependents? Example lang. Okay, so ibig sabihin there's something there might be something wrong with the model, and it can also be attributed to non-linearity of the relationship between the predictors and outcome variables natin. So, or pwede ring omitted variable. Ibig sabihin may kulang dun sa mga predictors natin. That's what we call omitted variable bias. Omitted. Sulat ko na nga lang. So, bilis. So here, omitted variable bias. Okay. Kasi if the predictors, if there are lacking predictors, so meron tayong omitted variable bias, and chances are this will result into a heteroscedastic distribution of your residuals. Okay, so aside from this is one of the most important plots here. Ito naman, this will now address yung question ng normality. Diba sabi natin, the residual should be normally distributed. And we can see here that dapat kasi malapit lang siya sa QQ plot natin. But you can notice here that at the mga higher values, kikita natin na hindi siya normally distributed. And again, these numbers here pertain to the observation number. So observation number 229, 59, saka 15. So these are candidates for outliers kasi i-check din natin yun, no? Kasi ang outliers, it can cause also heteroscedasticity. And this one, okay, residuals versus fit values natin. Kaso dito yung residuals natin standardized na. Ibig sabihin normalize siya. So pareho lang to ng una. Okay, but what we're just looking at here is the standardized. So it could also indicate heteroscedasticity. Okay, ganun din siya, no? Ayan. Diba? May fanning out. Hindi constant yung variance natin. So may problem yung model natin. Okay. So, time, allow me please just 2 minutes. Tapusin ko lang to. And also this one, residuals versus leverage. Okay, so andito yung Cook's distance. So next meeting, we're going to complete this. We're going to finish this. By the way, if you want, kung gusto niyo isang plot lang siya, no? Okay, isalin niyo na to par rows natin is equal to C to 2. So what does this mean? Ipa-plot natin yung yung ito, yung residual plots natin in 1. So we have 2 columns, 2 rows. Let's run this. Para kita natin sa isang plot lang. Oops, ayaw na. Okay. Sandali ah. Order kasi. Oh, mali ako. Dapat mo una si par. Control X. Uy, sorry. Sige, tama. Control D. Tapos ito. Alright. Dito, plot ng ginamit natin. Dito kinabay natin si partitioning. Ano? At saka din yung plot there. Okay. Notice the difference ha. Kanina kasi inuna ko yung plot tapos yung partition. Hindi niya na-partition. So ito pinartition niya in one plot. No? In one plot, 2 by 2, pinakita niya yung yung lahat ng plots in one plot. So makikita natin yung residuals versus fitted, yung standardized residuals versus fitted, yung normal QQ, at saka yung leverage. All right. So let me stop recording.